Since the assembly language depends heavily on registers, we discuss a few important functions of registers. One of the most important registers is the accumulator register that is part of every modern computer system found in the market today. It is used with instructions such as add, subtract, etc. One important metric or measure that is often used in our daily life is the size of the machine. We say that the machine is a 32-bit machine or a 64-bit machine. So what does that mean? This measure or size is identified and defined by the size of the accumulator. Speaking in general, the size of the registers in the register file is what defines the size of the machine. One special class of registers is used to hold the address of the operands. So the register is not holding a value, it holds the address of the operand. We'll talk about this special class of registers, but just for understanding, for example, in loop control, if your data is not placed in consecutive locations in memory, then you would like to use pointers because using pointers you would have more control and would only increment the address rather than having to explicitly give the address of each location using instructions. Then we have the program status word, PSW, also known as the flag register. Flag is a 16-bit register. Its 32-bit version is E flag. E stands for extended, and R flag is its 64-bit version. It is very important and central register in any architecture. It's a collection of different Boolean information. Each bit has an independent meaning, and combined it is meaningless. So combined it has no meaning, but independently it is used by the processor to implement complex logic. For example, loop control, rounding off, saturating the result, etc. So whenever an instruction is executed, it changes the state of the state of the system, that is the PSW. So let's look into what each bit or flag really represent. So we have the CF. CF is the carry bit, which signifies any carry from the most significant bit of the calculated result using, let's say, the add instruction. Or we have any borrow from the adjacent bit in a subtract operation. So the instruction changes the status of this register as they get executed by the processor. And the processor reads this register to obtain useful information for handling different activities. Then we have the third bit. The parity bit is mostly used in error control in communication. The parity is the count of number of ones in a word. For example, if we are sending a word in which the number of ones is even, it means the parity flag is 1. If the word is received with an odd parity, odd number of ones, then we can be sure that some error has occurred. Then we have the AF, auxiliary carry flag. This is the status of the carry from lower nibble to higher nibble. This bit is used in 8-bit operations. The 0 flag, ZF, this bit is set if any arithmetic or logical operation produces a 0 result in the destination. This is useful to compare two values for loop control. We will look into loop control stuff in detail when we grasp some idea of assembly. The sign flag in 2's complement representation, if an arithmetic or logical operation is carried out on signed numbers, the status of this flag is set if the most significant bit of the destination is 1, and vice versa. Interrupt flag, this set the priority of interruption from the external world. Whether we want to be interrupted or not is decided by setting or clearing this flag. One important fact about this flag is that this is not in control of the processor because the user really knows when to interrupt and when not. The direction flag, DF, this flag controls the direction of memory accesses. If it is set to 0, then we are moving from lower addresses towards higher addresses. And when this is set to 1, then we are moving from higher addresses towards lower addresses. This is especially useful with string operations such as copying strings and comparing strings. These are the control flags. Control flags are used for various uh, activities. The overflow flag, this is a very useful flag that signifies the overflow status to caution the user that the sign of the result has changed unexpectedly. If we add two 4-bit signed numbers that is represented in 2's complement, the sign in the resulting register changes unexpectedly. So this flag is set high. For example, the highest number in 2's complement that could be represented in a 4-bit sequence is equal to 7. If you would add 1 to it, 7 plus 1, that would generate a carry bit all the way to the 4th bit, resulting in changing the sign bit from 0 to 1. The status of the overflow flag would caution the user to take corrective measures. So this flag is used with signed numbers representation in 2's complement. So these are the general purpose registers. Earlier in this slide, we discussed the special class of registers used for holding the address of the operands, the pointer, index, and base registers. Historically, people thought to have special purpose registers for their architectures, but in modern processors, to make things more versatile, they have generalized the use of these special purpose registers, which became to be known as the general purpose register, also abbreviated as the GPR. These general purpose registers are used for special purpose as well as for general purposes. So next we look into these general purpose registers that are named based on their specialized functions. We will discuss this in a later lecture. For now, you can see the naming conventions used by x86 processors. AX, BX, CX, DX are of 16 bits, and they are addressed by these names. Unlike in memory, where we need to give it an address that is a number. The 32-bit version is named EX, EBX, ECX, EDX. E stands for extended register. And RAX, RBX, RCX, RDX, though not shown in the graphics, but this stands for 64-bit version of the AX, BX, CX, and DX. The consistency in naming conventions throughout the evolution of x86 makes it compatible to their older versions. For example, an 8-bit or 16-bit program compiled using these naming conventions would run on a 32-bit machine as well. In a later lecture, we will discuss the evolutionary design benefits that is the main reason for its popularity. For now, just remember that these registers are very flexible and are byte addressable, 16-bit addressable, 32 and 64-bit addressable, which makes it backward compatible to its predecessors. If we refer to AX, it means that the 16-bit register is accessed, and EX means we want to use the 32-bit register. And within AX, we have AH and AL. That means high byte and lower byte. AH and AL are not new registers. It is a part of AX. Any change made to AH and AL will also change the contents of AX as well. As we said that every vendor has their own naming system, and the A in AX, EX, and RAX is used for accumulator. Similarly, the B, BX, EBX, and RAX is used for base because it is used as a pointer to memory locations. That is why it is called base register. C is basically for counter. There are some instructions that automatically are used with count, and that count is placed in the CX, EX, CX, ECX, and RCX register. So we can see the sequence ABC, but they also have a meaning to it. Similarly, the D in DX, EDX, RDX is used for the destination of IOs. And we will see examples that will explain in detail the meanings of internal registers. These registers can also be used as general purpose registers. This is another way of viewing registers. We can see that we have the SI and DI registers, which are index registers, source index and destination index. Source index is used when we are referencing a memory location for reading. and destination index are used for writing something into the memory. However, these registers can also be used for general purpose operations by the instructions. The 32-bit and 64-bit versions of these registers are named as ESI, EDI, and RSI, RDI, respectively. Then we have a very important register known as the instruction pointer IP. The instruction pointer is a 16-bit register that is not shown on the screen. 16-bit register that contains the address of the current instruction memory. EIP is the 32-bit version, extended IP. We don't have much control over this register. It is only controlled by the processor and cannot be used for general purpose computations or accessing the memory by any other instruction. This is kind of a dangerous register, right? So then we have a very important register, the SP, which stands for stake pointer. ESP and RSP, extended stake pointer and RSP. These are the 32 and 64-bit versions. SP stake pointer is a memory pointer, but the user cannot use it for any other use. It is only used by some instructions, and we will discuss this in detail in other lectures. But for now, just remember that this register points towards a special segment in memory called the stack. Similarly, x86 has the base pointer registers BP, EBP, and RBP, which also points to a special region in memory. But it also cannot be used by the user. Only a few instructions use it to reference a special region in memory called the stack. Depending on the word size of the machine, these registers, i.e. the SP and BP, are used in their entirety. Unlike the general purpose registers that are also byte addressable, 16-bit addressable, 32-bit addressable. However, the stack pointers and base pointers can only be used as a whole depending on the machine word size. Having discussed the register structure of x86 ISA, it's time that we have some hands-on experience with some assembly programming language environments, some critical facts and mysteries around them. This is a simple program. So in the pseudocode, we simply write a program in English. We say move constant 15 to 16-bit register AX, and move 10 to 16-bit register BX. Then we add BX to AX and store the result in AX. Again, we move 20 to BX and add it to AX and place the result in AX. That would be 35, right? In the center, we have the assembly code. We can see the Intel assembly instructions, which simply resembles the pseudocode with only some rules and convention of the Intel processor. These rules are what becomes the ISA, and the assembly language programming needs programmers needs to understand these syntaxes. The Intel convention says that move move AX5. It means move 5 into AX. So the destination is in the left side, and the source is on the right side. So it means that the destination is on the left side. This is by convention of Intel assembly syntax, and the source is on the right side. Similarly, move BX 10. Move 10 into BX. The third instruction says that add BX to AX and place the result in AX, because by convention, the destination is on the left side. So that is how a logic is implemented in the assembly language. So in the Intel assembly instructions, some have both source and destinations, while some may only have destinations or only source. Like some instructions, by default, uses some registers meant for special purpose. Like the loop uses the count register by default. We will talk about assembly syntaxes and a broad spectrum of instructions to familiarize you with assembly. But for now, I'm sure at least this simple example must have reduced your fear of the assembly language. Nobody can say that this is a difficult program, right? Now, to have a feel of assembly, we would want things running before our eyes. So let's dive into assemblers, IDEs, and debuggers that must be under your belt if you want to code in assembly. We will be using SASM, which is an open source IDE licensed under the GNU project. Uh, this is uh, 4-in-1 assembler IDE that supports both the Intel syntax, assembly syntax, and the GCC at assembly syntax. These are the two versions of assembly that have very minor differences, and no version has any advantage over the other. It is just a matter of convenience to different audience. It is like different accent to the same language. Only there is a little format change.